lecture, we are going to describe trust region methods for unconstrained optimization problems. So far, in any of the optimization algorithms that we have described, we proceeded in the following manner. From a given iterative point xk to move to the next iterative point xk plus 1, at first we identify a descent direction at the point xk, and then we take a step of certain amount of length along the direction, and accordingly we move to the next iterative point. This is how we have proceeded so far. However, in trust region algorithms, this process is almost reverse. At first, from a given iterative point xk, we provide a maximum allowed step length, and this maximum allowed step length at the iterative point xk identifies a circular region or a spherical region centering at the point xk. Then inside this circular or spherical region centering at the point xk, we take a best possible step in the trust region algorithm. So at first, the length and then a step is followed in trust region algorithms. So let's start in this lecture, where we will describe at the end of this lecture two particular trust region methods. Those are dogleg and double dogleg method. Let's start. Neatly agendas of this lecture are 3 points. The first, essential terminologies to describe trust region methods. Those are trust region, model function, and a reduction ratio. Trust region is a region in which we trust a model function to approximate the objective function of the optimization problem under consideration. How good is this approximation is identified with the help of a ratio value called reduction ratio. Reduction ratio value indicates when to shrink and when to expand the trust region. With the help of these three concepts, trust region, model function, and reduction ratio, we will describe a general structure of trust region algorithms. That is the second agenda. We will see that in moving from one particular iterative point to the next iterative point, we will solve an optimization problem where we will consider to minimize the model function subject to the trust region at the current iterate, and this particular optimization problem at the current iterate is called trust region subproblem. In realizing global convergence of trust region algorithms, we will see that only an approximate solution to the trust region subproblems will suffice, and therefore in the third agenda we will attempt to approximately solving trust region subproblems, where we will first describe the concept of Cauchy point. With the help of the notion of Cauchy point, we will describe two particular trust region methods in this lecture. Those are dogleg and double dogleg techniques. Let's start. In describing trust region methods, we consider three standing assumptions. Those are: the first, the objective function of the problem under consideration is twice continuously differentiable. The second point is that for a given initial point x0, the objective function f is bounded below in the initial level set L0. The third is that the Hessian of the objective function is uniformly bounded by a constant beta with respect to a matrix norm. These three assumptions are not only required for the description of the trust region methods, but also they are required in realizing global convergence of trust region methods. So far, in any of the optimization algorithms, we proceeded as follows to execute the iterative points. If xk is a general iterate, then to move to the next iterate, we consider to identify at first a descent direction dk say of the objective function at the point xk. After identifying the descent direction dk, we go for finding a step length alpha k to be taken along the direction dk. Accordingly, we reach at the point xk plus 1 given by xk plus alpha k dk. So we have followed two steps consecutively. The first one is identification of descent direction. The next is identification of a step length. In trust region methods, we almost reverse this process. At first, in the first step, we provide a maximum allowed step length delta k, and then we move for finding a step to be taken. We notice that at a given iterate xk, if we provide a maximum allowed step length, say delta k, then this delta k will identify a set of points which are not more than delta k distance away from the point xk. Let us denote this region of points having distance not more than delta k by tk. This tk can be presented by set of vectors p such that norm p is less than equal to delta k, where we consider p as the vector x minus xk. After identifying this tk, we find in the second step the step pk to be taken by minimizing a model function which can act as a model to approximate the objective function in the trust region tk. Now here we notice that this model function is such a function which can be trusted as an approximation of the function f inside this region tk, and thus this region tk is called trust region. TR is an abbreviation of trust region. Accordingly, this delta k is called trust region radius. As pk will be used to identify the next iterate, we name this pk as trust region step. Identifying pk, we update the iterative point xk to xk plus 1 given by xk plus pk if mk is a good model function, is an adequate approximation of f inside the trust region tk. If however mk is not a good model function, then in that case we keyfold the current iterate and the next iterative point is the same as that of the earlier iterate. So if mk is not a good approximation, then we consider xk plus 1 to be xk. Now here we notice that mkp is playing a crucial role to identify the next iterate. Question comes, how do we find this mkp? We notice that we have considered the first assumption that the function f is twice continuously differentiable. Then we can employ the equation of Taylor's quadratic approximation, around the point xk to find a good model function mk to approximate the objective function f. The equation of Taylor's quadratic approximation around the point xk is as follows: fk plus gk transpose p plus half p transpose Hessian at xk plus a fraction multiple of p multiplied with a vector p, where this xi k is a scalar in between 0 and 1. From this equation of Taylor's quadratic approximation, we take the model function to be the expression fk plus gk transpose p plus half p transpose. Instead of considering this Hessian matrix, we employ an approximation of it. Let's suppose bkp. Here, in taking approximation of the Hessian, we do not consider much condition on this bk. We just consider this bk is symmetric and the sequence of Hessian approximations across the iterative points xk's is uniformly bounded with respect to the same matrix norm that we have used in the third assumption. Now, as Hessian matrices of the objective function are uniformly bounded and the sequence of Hessian approximations are also uniformly bounded, we notice that the difference between fxk plus p minus mkp is of big O norm p square, and therefore as smaller the value of norm p, that better is the approximation mk for f. Now we notice that all this scene of approximating the objective function f by mk is going on inside the trust region tk, and inside tk norm p is less than equal to delta k. So if we alter the value of delta k, we get a possibility of altering the value of norm p. So by taking a smaller value of delta k, we have a smaller value of norm p, and accordingly the better is this approximation. But we notice that if mk can act as a good model function inside a smaller region, the same model function we may wish to continue for a bigger region, because in a bigger region, if the same model function can act as a good approximation, then the step pk can be chosen a step outside the trust region, so that we have a chance of getting a bigger length of this step, and once we have a bigger length of the step, then we have a good chance of reaching the optimum solution in a smaller amount of time. So what could be an wise choice of this value of delta k? We choose delta k by the following rule. If there is a good agreement between the values of mkp and fxk plus p, then we choose delta k as large as possible. However, for low agreement between the objective function value and the model function value, we choose a smaller delta k. We base this choice of agreement of the objective function and the model function by a ratio of actual reduction and predicted reduction. Actual reduction is the reduction of the objective function, and the predicted reduction is the reduction of the model function due to the movement from the iterate xk to xk plus pk. Actual reduction is then given by the difference fxk minus fxk plus pk, and the predicted reduction is given by mk origin minus mk at pk. Here you notice that at xk in terms of p we have 0, and in terms of pxk plus pk is pk. As the model function is defined in the variable p at xk, obviously then we have the model value as mk0, and at xk plus pk we have the model value as mk pk. We notice that as this pk, the trust region step is identified by minimizing the model function inside the whole trust region tk, and inside this trust region this origin is already inside the center of the trust region. Therefore we notice that this mk value at pk is certainly less than equal to mk at origin, and therefore the expression in the denominator of this ratio is certainly a non-negative quantity. And effectively then, by moving from xk to xk plus pk, we get a reduction of the model function. That's why we call the denominator as a predicted reduction. As we are using the term reduction for the model function, we continue to use the same term even for the actual difference of the objective function. This difference of the objective function value is called casually as a reduction, and thus it is named as actual reduction. However, this numerator value can be anything. It can be positive, it can be negative, or even be equal to 0. Now notice that when this rho k value is almost equal to 1, in that case the actual reduction is eventually almost equal to the predicted reduction, and therefore we can think of that model mk is acting as a good approximation of the objective function. If however rho k value is very close to 0 or even be negative, in that case we are very upset, because in that case the model function as a good model function to approximate the objective function in the neighborhood of the point xk. So we base the choice of happily saying whether a model function mk is a good model to approximate. We provide a threshold value. If rho k value is bigger than a threshold eta 1, then in that case we can expect that the model function is a good approximation, because when rho k is greater than eta 1, the actual reduction is greater than this fraction eta 1 times the predicted reduction, and therefore effectively we are getting a bit of reduction of the objective function value. Not always we are very happy with just a bit of reduction of the objective function value by the movement from xk to xk plus pk, and therefore we give a happy threshold value eta 2 when rho k is bigger than eta 2. Then this actual reduction is substantial, which is at least eta 2 times the predicted reduction. Here we choose eta 2 to be a happy threshold, which is greater than the smaller threshold eta 1. If however we notice that if rho k is less than this threshold value eta 1, then in that case actual reduction is smaller than even a fraction amount of the predicted reduction. So in this case we are very unhappy, and we cannot expect that the model function is a good approximation of the objective function. When we are happy with the model function mk, that means in the case when we have the ratio rho k is greater than the happy threshold, in that case we notice that mk is acting as a good model inside this trust region. So we can think of using the same model function even for a bigger region, and we may expect that in a bigger region the trust region can also act as a good model function. So we take a chance of enlarging or expanding the trust region in which we can even trust the model function as a good approximation. So we increase the trust region radius from delta k to a multiple of delta k, where this multiple is bigger than 1. If however this rho k is less than the threshold eta 1, then in that case we are not really happy with the model function, and therefore we have to reduce the norm p value, and therefore we have to reduce the trust region radius, so that in a small value of norm p we may expect that the model function is an approximation of the objective function. So when rho k is less than eta 1, in that case we reduce the trust region by a fraction of the earlier trust region, where gamma 1 is a fraction in between 0 and 1. So this is how we update the iterative point xk plus 1. After evaluating this xk plus 1, next step we move forward to identify delta k plus 1 by following this rule that I have mentioned over here. After identifying this xk plus 1 and delta k plus 1, again we move to apply the same steps that identify pk plus 1, identifying pk plus 1, again you identify rho k plus 1 and check whether it is greater than a threshold or less than a threshold. Accordingly you revise the trust region, shrink it or expand it, and move on computing xk plus 1, xk plus 2 and so on, until and unless we find a point at which the gradient value is almost is equal to 0. This is what the general structure of trust region method. Here is an algorithm of general trust region methods. We have in total 5 steps in this algorithm. The first step is on initializing the parameter values. We start providing at first an initial point x naught. We also provide a maximum allowed step length delta bar to be taken across the points, because if we do not provide a maximum allowed step length of delta bar, we may be very much aggressive, we may be keep continuing with expanding the trust region radius, and in that case we take a very aggressive step and maybe the method might not get converged to an optimum solution. So we take a caution step that we take we provide initially a maximum allowed trust region radius delta bar. We also provide an initial trust region radius delta naught. We provide a precision value epsilon, precision scalar. We provide the threshold value for the reduction ratio rho k. We also provide a happy threshold value eta 2. Here is a fraction to shrink the trust region radius, and here is a multiple gamma 2 to enlarge the trust region. Beta naught is an approximation of the Hessian of the objective function at the current iterate x naught. We initialize the counter, the iteration number is equal to 0, and then we move to the second step. Second step is on optimality check. We check whether the current iterate is possibly a stationary point. If not stationary, then we move forward to find the step. But if stationary, then in that case we stop and we output xk as a solution to the problem. When xk is not a stationary point, we try to solve this minimization problem, minimizing the model function mk inside this trust region, and find the step pk trust region step. we call a solution, an exact solution of this trust region subproblem as PK exact, subscripted capital E, which refers to exact. So if we are computing exact solution of this problem, then we are naming it as PKE. Taking this PKE as trust region step, we move to the next step where we go for updating the current point. To update the current point, we check the reduction ratio value. We find the reduction ratio value rho k and check if rho k is greater than the threshold eta 1. If greater than the threshold eta 1, then in that case only we use the trust region step to update the current iterate. And if rho k is less than equal to this threshold eta 1, in that case we do not use the trust region step to consider as the next iterate. So we keep hold to the current iterate. After updating the current point by following these two rules, we move forward, then resizing the trust region. Because here in this step 3, we have identified the next iterative point xk plus 1. And then we have to find then the trust region radius. This trust region radius has to be then found by following rule with the help of the reduction ratio. If reduction ratio is less than a threshold, then as we have mentioned that we are very unhappy with the model function as an approximation, then in that case we have to shrink the trust region so that in a smaller region we may expect that the model function amk can act as a good model. So we shrink the trust region by taking the next trust region radius as a fraction of the previous trust region radius. If however the trust region, if however the reduction ratio is bigger than the happy threshold eta 2 and the step PKE is lying on the boundary of the trust region, then we notice that if we take, we notice that we may feel that if we would have taken a bigger region of the trust region, then in that case it might happen that this trust region step would have lying in a bigger region, in the bigger region, and therefore when the reduction ratio is bigger than the happy threshold and the trust region step is lying on the boundary, then in that case we increase the trust region radius as a multiple of the previous trust region radius. But we have to be cautious here that this gamma 2 delta k must not be exceeding the maximum allowed trust region radius delta bar. So we update the trust region radius by taking minimum value of delta bar and gamma 2 delta. But in the case when rho k is lying in between the lower threshold and the happy threshold, or in the case when the reduction ratio is bigger than the threshold and the trust region step is still inside the trust region, then in that case we may not expect that that in a bigger region the trust region step will lie outside the previous trust region, and in this case then we do not alter the trust region radius. We just keep continuing with the same radius that we have used in the earlier, in the previous step. So here we notice that we have three cases. The first case is a very upsetting case. We call it an extremely bad case. The case when we are having a chance of improving the trust region or enlarging the trust region, we call it as an extremely good case, and the case when we do not alter the trust region radius, we call it as a moderate case. Here in the step 3, when rho k is bigger than eta 1, then we notice that the next iterate is updated by xk plus the trust region step. However, when rho k is less than equal to eta 1, we do not use the trust region step to be taken in the next iterate. When we take the trust region step as the next iterate, then that case is called a successful step. And the case when we do not use the trust region step, then in that case we call it as unsuccessful step. Well, so after resizing the trust region radius, after finding delta k plus 1 in the step 4, in the step 3 we have identified the next iterate xk plus 1. In step 4 we have identified the trust region radius for the next iterate delta k plus 1. And after finding this delta k plus 1, next in the step S5 we generate an approximation of the Hessian at xk plus 1. Then we increase the counter, the iteration number, and go for checking the optimality at the point xk plus 1. In the step 2 we check for optimality, we check whether the norm of the gradient at xk plus 1 is less than epsilon or not. If yes, then stop and provide xk plus 1 as your solution. But if is not less than epsilon, then in that case we move forward as we have followed in the previous step. So in this way we keep continuing the step calculations until and unless we get a point at which norm gk is less than epsilon. This is what the general structure of a trust region algorithm. Here we notice that the first question would arise after writing out this algorithm is that whether this algorithm is well defined or not. We notice that throughout all the steps, step 1, step 3, step 4 and step 5, we just have a few condition checking and updating of some iterates or some parameter values, but we notice that there is no question of existence of something, and we have a question of existence of the trust region step at the point at the second step, where we go for solving the trust region this subproblem, and accordingly we execute this PKE. Question would come, if PKE does not exist, then obviously we cannot move forward in the algorithm, and if does not exist, then obviously this algorithm is not going to be well defined, because this step cannot be calculated then. This PKE, this step cannot be calculated then. But you notice that this subproblem is a very special kind of subproblem. This is a minimization of a quadratic function which is a continuous function certainly, and subject to a compact constraint. Here this constraint region is a closed and bounded set in the n-dimensional Euclidean space, and hence a compact set, and hence by the Weierstrass extremum value theorem for continuous function there certainly exists a minimizer of a continuous function in a compact set. So this PKE certainly exists, and hence the entire algorithm is well defined. Well, the algorithm is well defined, fine. Then how do we go for solving this trust region subproblem? Is it always the case that we go for exact solution PKE? Certainly no. We will find that an approximate solution of this subproblem will suffice for global convergence. This algorithm is so nice that it has global convergence property even if we go with an approximate solution of this trust region subproblem. But provided that approximate solution, let's suppose pk, is satisfying a sufficient reduction condition that gives a sufficient reduction to the model function, which is identified by this inequality, that pk, an approximate solution of the subproblem, must be such that this inequality is holding, then we can ascertain the global convergence of the trust region algorithms. Well, so then how to find such a P for which this condition is satisfied? For that, we will discuss a concept called Cauchy point or Cauchy step. To identify this Cauchy step, then we notice that at first that inside this trust region subproblem, we have not talked about how do we compute this BK. This computation of this BK can be done just by employing the rules that we have described for quasi-Newton methods, where we have detailed how to approximate the Hessian matrices of the objective function at the identity points xk, xk plus 1 and so on. Now next we will describe a concept called Cauchy point to identify an approximate solution of the trust region subproblem at which this condition will be satisfied. Cauchy point is a point in the trust region which minimizes the model function along the direction of negative gradient of the objective function. That means in the trust region Tk, we find the negative gradient direction, and along this negative gradient direction we find a point of minimum of the model function. So we find a minimum of the model function along the negative gradient of the objective function, subject to, obviously, the minimum point must be lying inside the trust region. A solution to this problem is called a Cauchy point. We denote this Cauchy point by P K subscripted capital C, C for Cauchy, and this concept of Cauchy came out to honor the great mathematician Louis Augustin Cauchy due to his important work in the year of 1847 on steepest descent method. Now, how do we find this step PKC? To find this PKC, we try to solve this problem where we need to minimize the expression of mk for minus alpha gk is given by fk minus alpha norm gk square plus alpha square by 2 gk transpose bk gk subject to norm of alpha is less than equal to delta k by norm of gk. We are assuming here norm of gk is non-zero. We are assuming that the point xk is not a stationary point of the objective function. Now, solution to this problem can be found as follows. We notice that if we go for finding an unconstrained minimum of this objective function, then that unconstrained minimum is at this point, that alpha ku say is, we notice that if this gk transpose bkg is greater than 0, then in that case the second derivative of the objective function is always positive, and we can find a point of local minimum by considering its a stationary point, and a stationary point for this objective function is given by norm gk square divided by gk transpose bk gk, provided the denominator is positive. However, if this denominator gk transpose bk gk is not positive, then in that case we notice that we can take infinitely large value of alpha. Accordingly, this objective function value gets arbitrarily large negative quantity, and hence in that case alpha ku is given by the value positive infinity. But as in this constraint optimization problem, we need to have norm alpha not exceeding this amount of value. Therefore, a solution to this problem is given by alpha k c is equal to minimum value of the unconstrained minimum and the restriction for alpha delta k divided by norm gk, and therefore perfectly this alpha kc is given by when gk transpose bk gk is greater than 0, then in that case alpha kc is given by norm of gk square divided by gk transpose bk gk, and minimum value of this together with delta k divided by norm gk, and when gk transpose bk gk is not greater than 0, then in that case the solution will lie on the boundary of the trust region, that is delta k divided by norm gk. So once we have found this alpha kc, then the Cauchy step pkc is given by minus alpha kc times the gradient of the objective function. This is called a Cauchy step for the trust region subproblem. We shall know an interesting fact for this pkc, which will be stated as a lemma, that the Cauchy step pkc satisfies the sufficient reduction condition mk0 minus mk pkc is greater than or equal to half times norm gk times minimum of delta k and norm gk divided by norm bk, and proof of this lemma is very much straightforward. We just execute this expression mk pkc, that means we just plug this expression of pkc in the model functions expression and just employ Cauchy-Schwarz inequality. You will find that this inequality is holding. We do not have much time to prove it, but for a detailed proof, you please visit the lemma, the proof of the lemma 6.1.4 on page 310 of the Great Sun and One's book. Then lemma 1 is a great result, that we have found a point inside the trust region, this point PKC, such that at this PKC we have this condition of sufficient reduction holding for the beta 1 value is equal to half. That's great. Then we can just take PKC as a trust region step instead of using this PKE. We use PKC, and as PKC is having a sufficient reduction of the model function, then we can just replace this trust region subproblem by this Cauchy point subproblem, and accordingly the revised algorithm will be named as Cauchy point method, Cauchy point trust region method, which is a globally convergent trust region method. Fine. Now here you notice that if we keep on employing PKC at each and every iteration xk, then you notice that we are just following the steepest descent method, because to evaluate the Cauchy step PKC we just identify a minimizer of mk along the negative gradient direction. If we follow negative gradient direction at each and every iteration, then obviously we are just following the steepest descent direction method. And as steepest descent direction method is known to have slow rate of convergence, this Cauchy point method will then become a very slow method to reach at an optimum solution to the problem under consideration. Then we can try to improve this Cauchy point. And how do we improve this Cauchy point to have a faster rate of convergence? We notice that in executing Cauchy point, nowhere the role of BK is taken in the steps. Only we consider this BK to be used in evaluating the step length but not the step direction. Inside the step direction, then we have to somehow involve the Newton scheme so that the method may become a fast method to reach an optimum solution. So how do we do it? The To improve the Cauchy point, or to improve the trust region step inclined towards Newton step, or to involve BK in the calculation of the trust region step, we at first assume that the approximated matrix BK is positive definite and hence it is invertible. Once BK is invertible, the quasi-Newton step is given by BK inverse GK together with multiplied -1, and we denote it as PKN as if it is the full Newton step or full quasi-Newton step. And the direction of negative gradient is as shown in this figure. This entire scene is in the p variable space. In this figure, let us suppose the location of Cauchy point is over here. This is the Cauchy point, say PKC. To improve this PKC, to make it inclined towards the Newton direction, let us at first try to analyze the optimum solution of the trust region subproblems location for varied values of this trust region radius. Let's suppose we are considering a smaller value of delta k, then in that case we notice that we have norm p value is smaller, and accordingly this second order term in the model function will have low influence in the optimum solution. So this trust region subproblem will almost behave like minimization of a linear function subject to norm p less than equal to delta k when delta k is small. And we notice that solution of this minimization problem discarding this term is given by, you just employ here usual Cauchy-Schwarz inequality. We will get the optimum solution point as the point minus delta k. It will lie on the boundary because it is a linear function fx plus gk transpose p. Certainly this optimum solution point is given by negative delta k gk divided by norm gk. Fine. So it will be almost close to this negative delta k times this unit vector along the direction of the gradient g, and hence for small value of delta we have the optimum solution lying almost close to this point intersection of minus gk with the boundary of the trust region. So let's suppose this is the point uh, which is the optimum solution of this trust region subproblem for this much amount of value of delta k. If we enlarge the value of delta k, then we notice that this second order term will start influencing in the optimum solution, and when delta k is big and big, then when very big value of delta k we consider, then we notice that this full Newton step pkn will be inside the trust region, and in that case the full Newton step will be the optimum solution when delta k is chosen to be this much amount. And therefore slowly when we increase the value of delta k, this optimum solution to the trust region subproblem will be inclined towards the Newton direction. So an hypothetical trajectory of the optimum solution will be something like this graph. This is the trajectory of optimum solution points for the trust region subproblem for varied values of the trust region radius delta k. Let us afresh redraw this figure for a given delta k to understand how do we take an approximate solution then the Cauchy point, so that approximated solution is inclined towards the Newton step. Here we notice that the PKE point, the exact solution of this trust region subproblem, the solution PKE is intersection of the boundary of trust region for a given delta k with this orange graph. So this intersecting point is the location of pk exact. Now let us afresh redraw this figure. Uh, Here is a fresh drawing. We notice that for a given delta k, this region is the trust region, and here the location of pkc is over here, pkn is this full Newton step. Now to find an approximate location of this exact solution's location is over here, that is your pk exact. To find an approximate location of this pke, what we do is we join this pkc with this pkn with a line segment and find the intersecting point of this line segment and the boundary of the trust region. We take this intersecting point, call it pkd, as an approximation of this pke. From this graph itself we see that how close this pkd and pke. This D subscript has a very special significance. This D is for dogleg technique. Here we notice that the line segments joining the center of the trust region and Cauchy point together with this line segment joining PKC and PKN, these two line segments together look like a dog leg, and thus this intersecting point of this line segment joining PKC and PKN and the boundary of the trust region is called as a dog leg step. Dogleg trust region step. And you might ask me a question that what is the certainty that this line segment PKC, line segment joining PKC and PKN will certainly intersect the trust region? Uh, cannot we have the location of PKN over here, and so that the dog leg will look like a folded leg, and in that case obviously the line joining PKC and PKN will not intersect the boundary of the trust region. No, this such case will not arise. We can prove that the distance from the center of the trust region to the Cauchy point is always less than or equal to the full Newton step. This proof is just a simple application of Cauchy-Schwarz inequality. We just plug the expression of PKC and we get the following, that PKC is given by norm of minus alpha k c gk, and we notice that this alpha kc is given by minimum of two quantities that we have executed already. For as we are assuming here this bk is positive definite, so we have gk transpose bk gk is positive, then we have alpha kc given by minimum of two quantities. Please revisit the earlier locations where we have given the expression of alpha kc, minimum of two quantities, and therefore this alpha kc modulus value is less than equal to modulus value of any of the two quantities over here, and hence this alpha kc times gk will be less than or equal to norm gk cube divided by gk transpose bk gk, and this will be less than equal to gk cube norm divided by gk transpose bk gk multiplied by the fraction norm gk times bk inverse gk divided by gk transpose bk inverse gk. This is due to the Cauchy-Schwarz inequality. Now here we see that this portion, this BK inverse GK, is the full Newton step PKN, and this norm PKN is then factored with some expression GK cube divided by GK transpose BK GK times GK transpose BK inverse GK. Now, denoting this entire fraction as gamma k, we have this expression equal to gamma k times norm pkn. Now, I am giving a home task here. This gamma k is certainly greater than 0, and can we prove that this gamma k is less than equal to 1? This is just a simple application of Cauchy-Schwarz inequality. Try to prove it on your own. I am keeping aside as a home task. And once this gamma k is less than 1, then we have this less than equal to norm pkn. So Cauchy step is always a smaller distance away than the Newton step, and therefore this portion of the dog leg will certainly intersect the boundary of the trust region, provided PKC is on the boundary or outside of the trust region. Fine. So we follow the following rule to take the dogleg trust region step, that if the Cauchy point, if the Cauchy point is outside or on the boundary of the trust region, then you go with the dogleg step as this point intersection of the negative gradient together with the boundary of the trust region. Fine, if the Cauchy point is outside the trust region. If however Cauchy point is inside the trust region and the Newton step is outside the trust region, then in that case you take the intersection of this line segment together with the boundary of the trust region to take the dogleg step, that is this portion. If however, if the Newton point, full Newton step is inside the trust region, in that case we go with taking the full Newton step as the dogleg step. So this is the rule for taking dogleg trust region step. Now revising the PKE, the exact trust region step, by PKD, we can revise the entire trust region algorithm that we have discussed earlier, and accordingly we name that trust region method as dogleg trust region method. Now, in order to make this dogleg step still more inclined to the Newton step, we can proceed as follows. We consider a point which is lying in between this line segment, the portion of the Newton step which is outside the trust region radius. A point may be considered as this particular point, and we name this particular point as, let's suppose, PKN cap, and instead of considering the line joining PKC and PKN, we join PKC and PKN cap and take the intersection point of this line segment with the boundary of the trust region as your trust region step. We name this step as PKDD. DD has a very special significance. DD stands for double dogleg. This is due to the fact that we notice these three line segments joining center to PKC, then PKC to PKN cap, and then PKN cap to PN. It looks like broken leg of a dog. and this is called as double dogleg, and thus this intersecting point, and accordingly this pk double d is called the double dogleg step. Now here you might ask a question, how to find a point pk in cap, an auxiliary point to find the double dogleg step. This pk in cap can be chosen as gamma k pk n. The gamma k value is as executed over here. This gamma k value is in between 0 and 1. So if I choose my pkn cap to be gamma k pkn, then certainly we notice that we have norm pkc is less than equal to norm pk n cap. Then there will be a certainty that this portion will have intersection with the boundary of the trust region, provided pkc is inside the trust region and pk n cap is outside the trust region. So here we proceed finding pk double d by following a similar rule as it was for pkd, where pkd will be revised by pk double d. Here instead of pkn we should have pkn cap, and here also pkn cap. This also is pkn cap. So this is what the revision of dogleg step to double dogleg step. We notice that this double dogleg step is more inclined towards the Newton direction than that of dogleg step. In dogleg step, we notice that the location is this location, intersection of this line segment together with the boundary. So this was the location of PKD, but PK double D's location is this one, and therefore you notice that PK double D is a bit inclined towards the Newton direction. We could have taken this gamma k revised by some value, let's suppose eta k lying in between less than equal to 1 and gamma k. If we take eta k is equal to 1, then we notice that this double dogleg step will give us the dogleg step, because for eta k is equal to 1 we have this gamma k, this eta k pkn is equal to pkn, and therefore the double dogleg step will be identical to the dogleg step. So this is how dogleg and double dogleg methods work. In the original algorithm of trust region algorithms, if we revise the point pke by pk double d, accordingly we name that trust region method as double dogleg method. This double dogleg technique was due to Dennis and me, which came out in the year of 1979 in the Journal of Optimization Theory and Application. This is the paper where this double dogleg technique is found. This dogleg technique, the notion of Cauchy point, even the idea of trust region method is pioneered by great optimizer, great mathematician Michael James David Powell, who was a British mathematician who worked in the University of Cambridge, and he was a Danzig Prize winner. The Danzig Prize, is given every 3 years to one or more individuals for research which, by virtue of its originality, breadth, and depth, has a major impact on the field of mathematical programming. This prize is named in the honor of George B. Danzig, the father of linear programming problem, and is awarded jointly by the Society of Industrial and Applied Mathematics and the Mathematical Optimization Society. This Danzig Prize was established in the year of 1979, and the first prize was awarded in the year 1982 to Professor J.D. Powell and Professor Ralph T. Rockefeller. And Professor Rockefeller is now still alive. He is 87 in this year of 2022, but unfortunately Professor Powell is no more, who was 78 at the day 19th April 2015, where in that day we unfortunately lost Professor Powell. Now I end up this lecture by mentioning a few parameter values, a few common values of the parameters in the general trust region algorithm. Common choices of the parameters involved in the first step of trust region algorithms are as follows: delta bar is equal to 1, delta naught is equal to 3 by 4, epsilon is as per your requirement of how many decimal places you need to be correct for norm g is equal to 0. So here we keep as 10 to the power minus p for some positive integer small p. Eta 1, the threshold value for reduction ratio is assigned to be 25%. Eta 2 is equal to 75%. Gamma 1, the shrinking factor of trust region, is assigned to be half, and the expanding factor is assigned to be is equal to 2. With the help of these few parameter values, on the next lecture we will consider a numerical example to be executed with the help of dogleg technique. In the next lecture, after executing a numerical problem, we will provide global convergence result for trust region algorithms. There we will find that if we employ in the second step, if we employ a trust region step pk, for which we have this sufficient reduction condition holding, then with that step pk, the trust region method globally converges. That means you take a step pk as an approximate solution to the trust region subproblem, so that pk satisfies this sufficient reduction condition, then that trust region method globally converges. This interesting result we shall prove on the next day. And I end up this lecture with asking a question. The question is as follows. Well, we have described the entire trust region algorithm, the quasi-point concept, the concept of dogleg, double dogleg steps, and so on. But nowhere we have described whether this trust region algorithm is having the descent property. Can you have a thought over it and check whether this trust region method is having the descent property? Well, now I extend my heartfelt thanks to all of the viewers to view this lecture. Thank you. Thank you all.